In this video, we will guide you through the process of creating an AADL model with behavior specifications and running the Sliced Behavior Analysis tool. For this example, we are going to start with a face data model. To do this, we'll install the OSATE face data model to AADL translator using the Install Additional OSATE Components option. We'll select the face data model to AADL translator and hit finish. This will take a moment to install and require us to restart OSATE. After installing the face data model to AADL translator, we will create a new AADL project called BALSA, and we will copy a face data model USM into our newly created BALSA project. After copying the USM, we'll right-click and select Translate to AADL, which will create 4 new AADL files. These files appear in the ModelGen directory. I'm going to start with the PSSS file that contains the face UOCs in the Platform-Specific Services segment. I'll right-click and select Open AADL Diagram, and OSATE will generate the graphical representation of the AADL model. We can also show the contents or new diagrams for individual pieces of that AADL model. Here we're looking inside the ADSB UOP process, which is an additional component inside of my face data model. We can do the same thing with the Portable Components segment, again creating a UOP package model. Now that we've imported our data model and created some initial diagrams, we're going to open up the face integration model. The standard BALSA face data model does not include a fully specified integration model. In this example, we are going to add components to the integration model in AADL to provide enough information to run Sliced. Here I've opened up a component editor for the integration model implementation. I'm going to add a processor. Note that face does not discuss processors, so I'm adding a new element that did not come from my face data model. In the AADL graphical notation, hardware items like a processor are shown in 3 dimensions, as you can see by the rectangular prism representing the processor. I'm also going to add a process. By default, the face data model to AADL translator creates 1 process per UOP. However, for this example, I'm going to put all 4 of my UOPs into a single process. In AADL, each face UOP is represented as a thread group. If I want to add UOPs to a process, I can drop a thread group subcomponent onto that process. However, as you can see here, I need to create a classifier for this process. Right now, proc is an anonymous process. I need to create a named process in an AADL file so that OSATE has a place to store information added to that process. I'm going to do that by going back to my integration model package diagram and adding a new process type classifier called BALSA process, and I'm going to add a process implementation for that classifier. In AADL, things have types and implementations, so you've just seen me add a BALSA process type and a BALSA process implementation. Now that I have added a named implementation for my BALSA process, I can add subcomponents to it. In this case, I am going to add 1 thread group subcomponent for each UOP that I'm going to have run inside of this process. To do that, I will go to the Subcomponents part of my palette and select Thread Group. These thread groups are added anonymously by default, but I can give them specific classifiers that will reference the UOPs I imported at the beginning of this video. In this case, I'm going to create a EGI thread group for my EGI UOP. I'm also going to create an air traffic control UOP thread group. After creating the anonymous thread groups, I go to the AADL Properties panel and select a classifier corresponding to these thread groups. This is how I connect my implementation and integration with what I imported from my face data model. Now that I've selected a classifier, I can show the contents of these thread groups that is inherited as defined by the face data model and imported into AADL files that you saw earlier. Note that each of these thread groups has a thread contained inside of it. The face standard allows for multiple threads per UOP, which is why the thread group is used for each UOP. Before I can run sliced, I need to complete the communication paths between my UOPs. To do that, I need to add a TSS. In this example, I'm going to use an abstract for my TSS, and I'm going to create connections that go from my UOPs to my TSS and data flows that go from one UOP to the other through my TSS. Again, if I want to add information to my TSS, such as a data port, I need to create a classifier for the TSS that can contain that information. As you saw me do before for the BALSA process, I'm going to add an abstract type classifier and an abstract implementation classifier. Once I've added classifiers for my TSS, I can add information to it such as connections or flows. Now that I have a classifier for my TSS, I can take this anonymous TSS and refer it to the classifier I just defined. Once I've done that, I can create ports on the TSS that will allow me to connect it to the UOPs. Here I'm dropping data ports onto it, one to receive input from the EGI and one to send that EGI data back out to the air traffic controller. I add connections using the connections portion of the palette. After I've added connections, I can provide information about data flows. In AADL, a connection is strictly from one point to another. A data flow can traverse many points. Before I specify a full data flow, I need to add flow sources and sinks. In this case, I'm adding them to my UOPs. I'm also going to add a flow path through my TSS. After I've added the pieces of the flow, I can create an end-to-end flow using the end-to-end flow specification tool. I do that by naming it and then selecting all of the components of the end-to-end flow in turn. Now we need to provide the behavior details for my UOPs. To do that, I'm going to select the EGI UOP and I'm going to show its AADL source. Because I selected the EGI subcomponent in a process, it brought me to that process. By selecting the Open Type option, I can jump to the thread group implementation for the EGI UOP. Here you can see the thread properties for that thread group. I'll set some reasonable defaults here. To use Sliced, you specify a state machine for each UOP using the AADL behavior annex. The AADL behavior annex has its own syntax, and you use it in an annex specification as part of an AADL model. Here I'm specifying a list of states associated with the EGI UOP. Sliced allows you to establish state machines either for individual threads or for UOPs. Here, I am listing the states for the EGI UOP. I have one state called run that is an initial state, and another state called done that is a final state. The EGI is a periodic thread, meaning this thread machine will repeat at a set period, in this case 1 second. Now I'm listing transitions. I have a transition from run to done that will be taken when this thread is dispatched. I'm also going to indicate that the EGI is going to write a message on the EGI to TSS port. Now we will do the same thing for the air traffic controller UOP. Again, we will go to its AADL source, and we'll jump to the implementation of the air traffic controller UOP thread group. Again, I'm going to add the behavior annex specification inside the air traffic controller thread group implementation. I'm going to enumerate the states associated with the air traffic controller UOP and transitions between them. Here we have an initial state of waiting for EGI data, and a final state of done. We are also going to have a transition from the wait for EGI state to the done state that requires a message be received on the communication path from the TSS to the ATC UOP. For this example, I've also added a start state that has a dispatch transition with no other conditions from start to the wait for EGI. Now we're going to look at the type definition of our air traffic controller UOP to get the name of the port that is required to receive information before we can transition to done. Here we have a syntax error because the default definition of the TSS to ATC manager port is a data port, and the AADL behavior annex requires event ports to trigger data-driven events, such as a transition. For this example, I'm going to modify the port definition. However, the more correct approach would be to change the face data model from which this UOP AADL was generated. Now I'm going to go back to the process we created earlier and associate it with the process implementation classifier that we created and populated in this video. Next, I will right-click on the integration model implementation and select Instantiate to create an AADL instance file. Then I can click the Behavior Analysis button to run Sliced. Here we see that Sliced completed successfully. Sliced creates behavior models that appear in the derived model behavior directory. Selecting one of these models allows me to choose the behavioral display option, which will use Papyrus to generate a graphical rendering of the state machine defined by Sliced. However, in this case, I forgot to do one important step, which was associating the processor to the process running on it using something called a binding. To fix that, I'm going to go into my AADL source and create a processor binding property that associates the process we defined to the processor. This time I'm going to use the outline to instantiate this model. Again, this creates an AADL instance model on which I can run Sliced. Sliced will run and again create a behavior integration model XML file. Again, I can display that XML file using the Sliced viewer. And here we see the composite state machine Sliced generates from the combination of my two UOPs. Sliced did not find any behavior errors in this model, so let's add an error and see how Sliced detects it. To force an error, I'm going to delete the portion of my behavior in which the EGI writes information out to be received by the air traffic controller. In this case, I'll do that by commenting out the transition and adding a similar transition that simply does not write to a port. After making that change, I'll again instantiate my model, and I will run Sliced. This time, Sliced found a failed assertion. I'm going to delete my old display, and I'll create a new one. Now I can click the drop-down next to the play button, and I can see the name of the failed assertion. By clicking forward through the trace, I can see that the air traffic controller thread never leaves the wait for EGI state.